Welcome to this new video. In this video, we're going to learn about snow and the energy that it takes to melt the snow and how much water we can get out of it. Let's start with problem 3.18. It says, imagine a big area covered in snow. This area is about 4 square miles big. The snow is 27 inches deep, but it's not solid ice. It's actually 40% water. If all the snow melted and turned into water, and none of that water evaporated, how much water would we have? We want to know the total amount of water in acre feet. To solve for this problem, we're going to use this equation, the depth of a snow melt equation, which is the depth of melt equals the density of the snowpack times the depth of the snowpack all over the density of the melt, or will be like the density of what is melting, which in this case is water. Um, so to solve for this, we're gonna be d sub m equals density of the melt. And for this value we're given that this is 40% or 0.4. The depth of the snowpack is 27 inches, and the density of the melt in this case is water. It will be 1 or 1 grams per cubic centimeter, right? So all we need to do now to find the depth of water that this snowpack is gonna produce will be 0.4 times 27 inches over 1. So the depth of the melt, it's about 10.8 inches. But we're being asked for the total amount of water in acre feet. So we're gonna have to solve for the runoff volume, and we're gonna use this depth and multiply it by the area, which is 4 miles square. And all we need to do now is conversion. So we have to cancel for inches. We want an acre feet, so we got the feet, and now we need to multiply miles to acres. So there are 640 acres in 1 mile square. So that way we cancel miles square and we got acre feet. And this is going to be equal to 10.8. So runoff equals 10.8 times 4 times 640 divided by 12. And that gives us 2,304 acre feet. And this is the answer for the first problem. Now let's go to problem 319. It says, using the US Army snowmelt equation, determine the expected daily snowmelt in acre feet per day for a partially forested 160 acre area. The watershed constant is 0.5. The average wind speed is 10 miles per hour. This speed is measured 50 feet above the snow. The temperature is 40 Fahrenheit, and the average daily rainfall is 0.4 inches per day. What this problem is trying to say is we're trying to figure out how much snow melts each day in a specific area. We have information about the size of the area, how much it rains on average, the temperature, how windy it is, and a special number called the watershed constant that helps us understand how quickly snow melts. We'll use a formula called US Army Snowmelt equation, and this is to calculate how much snow turns into water each day. As you can see, this formula considers the temperature, wind speed, and other factors to estimate the snow melt. This is the formula right here, 0.09 plus this value. These values never change. What the variables are the ones that are going to change depending to our case study. And what K represents is the watershed constant, that is 0.5 for us. We have U as the wind speed, I as the rainfall intensity, and T sub A as the temperature of the air in Fahrenheit degrees. Make sure this is Fahrenheit degrees. So to solve this problem, we're going to use that equation, and that will be K is 0.5, U is 10, 0.007, intensity in our case is 0.4, and then we have 40 minus 32. This is going to be equals to 0.09 plus all this first bracket is going to be about 0.0738, and the second bracket is going to be 8, and equals 68.4 inches per day. So technically all we need to do here is plug in the values. So now we need to convert inches per day to feet per day. So we just need to convert this inches per day time this is going to be equal to 0.0567 feet per day. And now we need to solve. It says determine the expected daily snow melt in acre feet per day. So we have the feet per day, we need to multiply that by the area. And we're given 160 acres of area. That is going to be about 9.07 acre feet per day of snow melt. And that would be your answer for this problem 319. For problem 320, we're going to use an IDF curve for the last part, but all this problem is asking is for the following 1 hour hydrograph measured at Baltimore, Maryland, what is the average intensity in centimeters per hour? Remember that a hydrograph is time versus is intensity versus time in the x-axis. So we have the times intervals and the intensity. So all part A is asking for is the average intensity, which would be just the average or of our intensity values, and that gives us 6.2 inches centimeter per hour. We're working with centimeters in this problem. Um, Part B says, what is the volume of rainfall in cubic meters and liters if the watershed is 4,000 square meters? So let's 6.2. So for part B, what we need to do is just get the volume, and we're gonna keep using this 6.2 centimeter per hour intensity to solve for part B and part C as well. So it will be that the runoff equals to 6.2 centimeters per hour, and we need to convert now those centimeters into meters. So there are 100 centimeters in 1 meter, cancel centimeters, and we need to multiply that by the area, which is 4,000 square meters. So we're gonna have a runoff of about 246.67 cubic meters per hour. And that's the answer for part B. So part B will be 246.67 cubic meters oh, per hour, right? And now per C is asking us for what is the approximate return period. So for to find a value, the return period value, let me make this figure. We're going to use this IDF curve, but we need to first solve for the in the intensity in inches per hour. We have it in intensity in centimeters per hour, so we just need to do the following conversion of 6.2 centimeters per hour, and there are in 1 inch there are 2.54 centimeters. So centimeters cancel, and we're gonna get about 2.43 inches per hour. And the reason why we're doing this is because to find the return period, we're going to need the rainfall intensity and the duration. But the rainfall intensity for this graph is in inches, so the centimeters won't work for us. So that's why we do that conversion. And for the duration, our storm lasts 60 minutes. So it will be about 1 hour. So with our new value of 2.43 inches per hour of intensity, which will be about somewhere here, and 60 minutes of duration. So it will be about crosses right on the 10-year curve. So that means that this represents about a 10-year return period. And that will be the answer for part C. Now for the last problem, we're gonna use some concepts of snow melting. So let's get started. We are given that it says if the available sensible conductive energy for the month of May is 600 calories per square centimeters per month, the available May radiation energy is 500 calories per centimeter square per month, and the rainfall depth is 12 centimeters per month, and the rain temperature is 15 degrees Celsius with plenty supply of May snow water content. We need to solve all this for these three questions. Let me explain really quick what all these types of energy uh, mean. So it says sensible conductive energy. This is the energy transfer that touches the snow. A great example is the wind. It's the energy that wind that goes right over the snow has. And in our case, in this problem, it says that during May, the energy was 600 calories per square centimeter. And now we have the radiation energy. This is the energy that comes directly from the sun rays, and gets in onto the snow, that reaches the snow, and that energy will be 500 calories per square centimeter in that month of May. And this is just the rain, the water rain that falls onto the snowpack. And it says that it rained about 12 centimeters in the May of month. It's also giving us the temperature, the rain temperature, because we're gonna need it uh, to solve later. Um, so let's start solving for part A. So to solve for part A, we're gonna have to need these values here. Actually, we only need this value here, but it's important that you know that to convert, this is an average, but to convert water from solid to gas, you will need about 600 calories per cubic centimeter of ice in our case. If it's solid, it will be ice. To convert it from ice to gas, it will be about 600 calories per cubic centimeter. And to convert it from ice to liquid, to melt it, you need about 80 calories per cubic centimeter. With those values, let's proceed solving for part A. Find the depth of melt water from the snow in centimeter per month due to the available energy and the warm rain. So the available energy that we have is the conductive energy, or like the wind, and the sun, the radiation energy. And it's also asking us to get it from the rain. So basically, we need to solve how much water the wind will produce. Well, how much water uh, the wind will produce from the snow melt, how much water will produce the sun rays, and how much water the rain falling on the snowpack will produce. And to solve that, we are gonna do it this way. So the depth of melt water. So first we're gonna do the conductive energy. That's the wind. So we have 600 calories per square centimeter. And to convert that to, how can I say, to make the ice into liquid, we need 80 calories. So we divide it by 80 calories per cubic centimeter. So we're gonna get, if you notice, this is square centimeter, this is cubic centimeter, so we're gonna get centimeters. And why we divide it is to see how many centimeters we get out of 600 calories per square centimeters of energy. So that's going to give us around 7.5 centimeters of water, or in this is depth, right? We're not including the area. So just is the depth of water in at this with this energy at whatever area that we have. Now, part two, this is just the part A. All of this is part A. Then the second energy is the what is it called? Radiation energy. That's the sun, right? So we have 500 calories per centimeter square. And also we're gonna use the same. How much energy we need to melt it to make a liquid is 80 calories per cubic centimeter. So that's gonna give us about 6.25 centimeters of water. And the last one is we need to know how much the rain falling on the snow, how much water it would produce. And we are given that we have 12 centimeters of rain. And the temperature of that water, it says, is 15 degrees Celsius. Now, it takes 1 calorie to raise the temperature of one, uh, I would say 1 gram of water to raise it 1 degree Celsius. So it takes 1 calorie to raise 1 gram of water 1 degree Celsius to raise it 1 degree Celsius. And 1 gram equals to 1 cubic centimeter. So this we can do 12 centimeters times 15 degrees Celsius times 1 calorie, oh, calorie, 1 cubic centimeters times, it will be, sorry, 1 degree Celsius times. So let's read here. It says the density of water is about 1 gram per cubic centimeter. So grams and cubic centimeter are not the same. This is weight and this is volume. So this equality is not like the same about what it represents. It's just like they are related. And then a calorie is the amount of heat it takes to raise the temperature of 1 gram of pure water 1 degree Celsius at sea level. So this is the relationship that we're using in this conversion. And from here, we can cancel our degrees Celsius, and we can cancel centimeters and one of this. And so we have two. So, and we divide all of this by the same way we did in our previous. We divided by 80 calories per cubic centimeter to see how much in depth, how much water in depth it's gonna be produced from the precipitation. And from here, we're gonna get about 2.25 centimeters. So the question is, find the depth of meltwater from all of these sources. So the answer will be just the sum of all of them. 7.5 plus 6.25 plus 2.25. And that should be about 16 centimeters of melted snow or water. So that's the answer for part A. Now, for part B, we're being asked how much will this total energy, including rain energy, available for snow melt cost per square meter if the price of energy were $0.12 per kilowatt hour. So in this part, we're gonna have to do a lot of conversions, and we're gonna use every single one of these values here. So a BTU is a British thermal unit, and it is a measure of heat content of fuels of energy sources. 1 BTU is the quantity of heat required to raise the temperature of 1 pound of liquid water by 1 degree Fahrenheit at the temperature that water has its greatest density. This is what a BTU means. Let's continue with the conversion to get how much money it will represent all these energies that we have plus the precipitation. So we already solved for the total. Okay, let's do B. We need to solve for the total energy in terms of money. So we have solved that we melted 16 centimeters. Now we need to multiply this by 80 calories per centimeter cube, right? Because we want to go back. We went from energy into depth. Now we want to make that depth, what it represents in energy, to see how much money that energy represents. So that's why we're multiplying by the energy needed, the energy that we use. Um, and then we want to convert those. So if we cancel this and this, we have centimeters square. We want to convert those centimeters square to meters. So we have 100 centimeters in 1 meter. And we want to have a square centimeters at the top. So we square this. So that way we cancel this, we cancel these square centimeters, and we now have calories per meter. So we multiply that by, we need to cancel calories. So we're gonna use 1 BTU over equals 252 calories. So we cancel calories now, and we have BTU per square meter. Now let's convert this BTU to kilowatts per hour. So we have that 1 kilowatt hour, no kilowatts per hour, kilowatt hour, sorry. 1 kilowatt hour is 3413 BTU. So BTU cancels, and now we have kilowatt hours per meter square. So if we convert, and we know that if we're given in the problem that we have, let me make it a little smaller. We have $0.12 per kilowatt, 1 kilowatt hour. So kilowatt hours cancel, and we're gonna end up with dollars per square meter. So if we plug all those values, we should end up with something like $1.786 per square meter, or just about 1.79, right? Dollars per square meter. And that's the answer for this part B. That's how much money it will it will that energy represents per square meter. Now for part C, we're being asked find the actual total runoff in centimeters per month from the watershed if the runoff coefficient is 0.2. So we're being asked for the runoff in centimeters, so in depth. So in these questions, we need to solve for the runoff. And if you remember, if we use our coefficient C, and if we have the precipitation in inches, we have our precipitation we solved, it was 16 inches. And if we wanted to have the runoff volume in as a volume, as a centimeters, cubic centimeters or cubic meters, we will multiply it by the area. But since in this question they're asking us for the centimeters per month only, so we don't need to multiply it by the area. However, this is, remember that this 16 inches is only what was produced from the energy used and the precipitation, right? So this runoff volume will be the C coefficient times the 16 inches produced plus the 12 inches that already precipitated. So we have to do 0.2 times 16. And sorry, this is not inches. I'm just used to use inches. These are centimeters. Centimeters. 16 centimeters plus 12 centimeters. And it's about 5.6 centimeters per month in the month of May. So this will be 5.6. And this is the solution for this last part. So yeah, this is it. I hope this is helpful for you. And see you in the next video.